Hello, everyone. I'm Haosen Liu. I'm from the Huazhong University of Science and Technology. I'm now interning at the SmartMore Corporation. It's my pleasure to introduce our work, Self-Supervised Image Prior Learning with GMM from a single noisy image. For image restoration tasks, the MAP-based framework is widely adopted. This framework consists of two terms. One is determined by the physical image model. The other is the image prior modeling, and this is the focus of our work. Generally, image priors are either human hand-designed or learned in a supervised way. Both of these two kinds of methods have their own drawbacks. For hand-designed methods, they are usually based on simplified assumptions. They cannot effectively capture the complex properties of natural images. For supervised prior learning methods, their performances highly rely on the collection of high-quality clean images. This requirement is sometimes hard to meet in practical applications. In this work, we propose to achieve the image prior learning directly from a single noisy image by imposing reasonable constraints. This type of method is called the self-supervised prior learning. As a learning method, it is more flexible and stronger than hand-designed methods. Besides, its learning process is free of the image collection burden. This makes it more practical than supervised prior learning methods. Here, we designed a self-supervised learning method for GMM. It has two modules. One is the prior learning module. It is achieved by the maximization of likelihood. Our question is, what will happen if we only use the prior learning module? We observe that, in this case, eigenvalues of the covariance matrix learned for GMM will be vulnerable to noise. To illustrate this, the histograms of eigenvalues learned from clean images and noisy images are both provided here. The figure on the left hand is for clean images, and the figure on the right hand is for noisy images. The difference of these two histograms clearly indicates that eigenvalues of the covariance matrix learned by the prior learning module alone are vulnerable to noise. Therefore, to suppress the influence of noise, the constraints module is necessary. Here, we propose two constraints. One is the coupling constraint. This constraint is determined by the noise assumption. When the noise is assumed to be Gaussian noise, it will only affect the eigenvalues. The second constraint is the sparsity constraint. It is based on our study on the statistic property of eigenvalues. As this histogram shows, most of eigenvalues for clean images accumulate around 0. That is to say, they are sparse. So, we adopt a sparsity constraint for eigenvalues. This sparsity constraint has a parameter L, which controls the level of this constraint. If this parameter L is too large, the sparsity constraint will be ineffective. If it is too small, the constraint will be too strong. For example, if L is equal to 0, all recovered eigenvalues will have to be 0. So, L should be set carefully. The determination of it will be introduced later. Incorporating these two constraints, our proposed self-supervised learning method for GMM is obtained. This method is essentially a constraint maximization problem. To optimize it, we firstly divide it into 3 subproblems. The solutions of these subproblems are provided here. Then, the original problem is optimized by iterating between these solutions. Now, we are going to consider the problem, how to determine the parameter L. Here, we propose to determine L with the equation 19. We observed that the equation 19 is to calculate the square of sigma, which is the noise level. Therefore, we think that a reasonable L should make the equation 19 equal to the true noise level. But the problem is, the true noise level is unknown. So, we replace the true noise level with an estimated noise level. In this work, we proposed a new noise level estimation method. This is based on our observation that for the histogram of NG values for noisy images, it peaks at the noise level and its peak region is locally symmetric. Therefore, we can estimate the noise level by averaging the NG values around the peak point. More specifically, this method includes 4 steps. Firstly, it divides NG values into several bins. This is to plot the histogram. Secondly, it finds the bin with the largest number of NG values. Thirdly, it selects several bins. This is to determine the peak region. Finally, it averages the NG values located in these bins, and this average value is the estimated noise level. Back to the determination of L, we estimate the noise level at first. Then, we increase L from 0 until the equation 19 is approximately equal to the estimated noise level. In conclusion, our proposed self-supervised GMM is summarized like this. At each iteration, it firstly does a coarse estimation of GMM's parameters. The covariance matrix will be further processed, where other parameters will be the expected results. Then, covariance NG values are used to estimate the noise level and to determine the parameter L. Finally, the NG values are corrected to suppress the influence of noise. In experiment part, we conducted various experiments to validate the effectiveness of our proposed method. This experiment is about the noise level estimation. Here, we compared our proposed noise level estimation with a SOTA method. For measurements we adopt here, the smaller they are, the better a method is. As this figure shows, it performs better than the SOTA method on all measurements. We further compared the histograms of NG values learned in different ways. In this figure, the blue curve is served as a ground truth. The red curve shows the influence of noise on the NG values. The yellow curve is the histogram learned from a noisy image with our proposed method. It coincides with the blue curve at most places. They are different only at small NG values. We experimentally observe that this small difference is not important. Therefore, it's reasonable to claim that our proposed method successfully suppresses the influence of noise. We also validate our proposed method on the image denoising task. This figure shows the image denoising pipeline we adopt. Briefly speaking, we learn the GMM with our proposed method at first. Then, the learned GMM is used to denoise an image with an existing framework. This figure shows the average performances of different methods on 2 sets of images. Among the self-supervised methods involved in the comparison, ours is the best. It outperforms the method S2S, which is the SOTA self-supervised deep learning method. Also, ours outperforms the method EPLL. This is very interesting, since this method can be regarded as the supervised counterpart of our proposed self-supervised method. The advantage of ours over these two methods can demonstrate the effectiveness of our proposed method. There are several visual results. As one can see, the results recovered by N2V, DIP, and S2S are heavily over-smooth. In this figure, the result recovered by ours is the only one that does not have obvious artifacts. In this work, we propose a key idea that we can learn the image prior directly from a single noisy image by imposing reasonable constraints. Under the guidance of this key idea, we have successfully proposed a self-supervised learning method that can learn GMM directly from a single noise image. Besides, we also proposed a noise level estimation method that can accurately estimate the noise level and help determine the hyperparameter error for our proposed self-supervised learning method. In the future, we will explore how to use this key idea to design self-supervised methods for other generative models, such as GAN and flow. That's all. Thank you for your attention.